Following on from the previous video, we got to this stage here. Where it's still unrealistic because the black particle is moving around really fast, and this one here is moving really slow. We need to somehow make this more realistic, and you really have to stare at this for a long time to try and determine what is it that would make it realistic. You have to stare at this for a long time, but if you stare at it long enough, you can see that to make it realistic, you have to get this arc length here to be the same as this arc length here. That will make it realistic, because if let's say a time t has passed, so the particle moved from here to here. Well, the particle of the second wheel will be somewhere around here. But where is this somewhere? Where is this somewhere? Well, this somewhere is when this arc length here is the same as this arc length here. That will then what will make it more realistic, because it's like me giving you this here. If you've got a circle, one revolution of this circle, let's say one revolution of this circle will take the particle to here. So this distance here, one revolution is 2 pi r. So this distance here is the same as the circumference of a circle. So that's the same along the same argument as this. If you have two wheels, rotating against each other, this distance here will be the same as this distance here. So for a given time, let's say 3 seconds has elapsed, the particle would have moved from here to here. It would have created this arc length. Well, the other particle will have been moved from here to here. So this angle, well, you need to work out this angle here. Let's call it beta. So for given c, for given c, we have to somehow work out this angle here, beta. But the condition is that this arc length will be the same as this arc length. Okay, so for given t, it has moved from here to here. That would mean that particle B would be right here. But we need to somehow think of a way of working out this angle, because if we can work out this angle, then we can work out the precise location of where the other particle, where this particle should be, if we can work out this angle. Okay, so the idea here is this: for given t, any time that has elapsed, so your job is to create a machine where we insert an angle t, or c in our case, it doesn't matter, put c into the machine, and then this machine will somehow generate the arc length. So you've got to somehow generate the arc length. Once you've got the arc length, create another machine where you insert, hang on, something's wrong with my computer, bear with me. You've got to create a second machine where you insert, once you've got the arc length, once you've worked out this arc length, you need to feed that arc length into a second machine. It would do something to give you the angle. It will give you this angle, let's call it beta. So it will give you beta. So this is your job. For a given angle t, you put it into a machine, it will work out the arc length. Once you've got the arc length, put the arc length into the other machine, and then it will then tell you the angle. So that's the angle. But let me simplify this. Let me just remove this, and we can just create a machine like this. So you work out the arc length. Once you've got the arc length, then you can just work out the angle. Once you've got this angle here, you can work out the precise location of this particle. So before we can do this thing, let me just give you some revision. So for a given angle, if you know the radius is a, then you can work out the arc length. But let me just give you some revision. So if I were to give you, I've got a circle of radius r and an angle of 23 degrees. How would you work out the arc length? Let's call it L. We've done this before. So what you do is you work out the whole circumference. So that would be 2 pi r. You cut up into, well, because we're working in degrees, you cut up into 360 equal pieces, and then you get 23 pieces. So you get 23 pieces. Because we work in radians, get 2 pi r, which is the circumference, cut up into 2 pi equal pieces, and then times in our case the angle here, theta. So now that will then give us L, the arc length. So now these two cancel each other out. So the arc length is really the radius times theta, where theta is in radians. Now let's go to here. Now if I give you the radius of a circle and the arc length, how would you work out the angle? Theta. So our job is to work out the angle theta here. So what we would do is, let's put it into a formula. 2 pi r, the circumference of the circle, cut up into 2 pi equal pieces, and then times theta. That should give you L. And our job is to work out the angle. So these two cancel each other out. So theta is really L over r. That will then give you your theta. So going back to here. Remember, hang on. Remember, for given t, we've got to, for given t, we've got to somehow work out the arc length, work out this arc length here, and then once we've got the arc length, which will be the same as this thing here, so once we've got the arc length, our job is to work out beta. So you feed the arc length into the second machine, and the second machine just spits out an angle beta. So that's our aim. So for given t, the arc length will be, well, what is this length here? Well, for given t, it would be this. Hang on. Work out the area, the circumference of the whole circle, 2 pi r, cut up into 2 pi equal pieces, times the angle t, and then, let me think, times the angle t, and then that will then give us our arc length, L. So now, so L is really equals to r, the radius, times t. That will then give us L. So this is the arc length, RT. But in our case, remember, our circle is radius A. So this is AT in our case, AT. So now let me erase this. Oops, how do I erase it? Hang on, bear with me. So now we've worked out the arc length is really the radius times t, radius times t. Now when you feed this into this machine, so now our second machine will need to do this. Bear with me. Our second machine needs to do this. Well, we know the arc length is AT. We've got to somehow work out the angle. And this angle here is B. This thing here is beta, the angle. The radius is B. So what we've got here is this. We've got radius of B, an arc length of AT, and our job is to work out this angle, beta. So let's try and work it out. So circumference, work out the whole circumference, 2 pi B, cut up into 2 pi equal pieces, and then if you times beta, it should give you the arc length, AT. So now 2 pi's cancel each other out. B times beta equals AT. So now if you want beta, then divide both sides by B. So beta equals AT over B. So this thing here is, bear with me, this thing here is AT over B. So what that means is, if you want to know this angle here, just so that you can locate this particle, if you want to know the angle here, for given t, if you want to know this angle here, what you do is you get your angle t, you times it by the radius of the big circle, which is A here, and then you divide it by the radius of the small circle. That will then give you your angle. That will then give you, oops, bear with me. Bear with me. That will then give you your angle AT over B. So this angle here is AT over B. So let's go back to here. So the location of the blue particle will be this. Hang on. So go to the blue particle. The angle would be this. Instead of the angle C, it would be AC over B. So it would be AC and then divided by B. Bear with me. You got to change the other components. You got to change the Y components as well. So bear with me. So it would be AC and then divided by B. So now, hang on, let's put C back to 0 and let's slow it down. Let's speed it up. So let's slide it back to 0. So press play. So now, hang on, still a bit too fast. Well, anyway, look at this. Look at the one revolution of the small circle. One revolution of the small circle would take the big circle, would take the particle in the big circle to be here, which is more realistic. So this length here is really the circumference of the green circle. So let me put it back to the start. Now look, one revolution of the small circle would equate to an arc length of this much. Okay, so you can see this is more realistic now because the two arc lengths are the same. If we force the two particles to have an arc length that are the same, then it would be more realistic. So this is more realistic now. The next question is, when will the next particle meet? Because at the moment, if you look at this, this particle, when will the next when will it be? What time will it be when the two particles next meet? Because they don't actually meet within, let's say, let me just do this for 3 revolutions. So that would be 6 pi. 6 pi. Let me get it to spin around 6 times. 1, 2, 3. I don't think they ever meet within the 3 revolutions. But my question to you is, when will it be? What time will it be when the two particles next meet? So look at this. Keep an eye on the black particle. So by the time it does 1 revolution, you can see that the two particles don't actually meet. Okay, let's do the second revolution. So going around again here. They don't actually meet, even though they look like they're going to meet. If I zoom in, bear with me. If I zoom in, they don't actually meet. Let me slow it down. Let me press play and then slow it down. Oops, it's gone too far. Where? They don't actually meet. Look, that's the first. I think that was the first revolution. Where there? Let me bring it around once more. They don't actually meet. See that? They don't actually meet. So let's one more. Hang on. See that? They don't actually meet there. The third time around, they don't actually meet. Well, anyway, what time will it be when they will both next meet? So wait there. So let me press play. So what time will it be when the two particles will next meet? At the moment, well, I'm going to let you stare at this for a bit. Okay, so that's the next question. First revolution. Let me slow it down. They don't actually meet. Let me speed up. Let me slow it down. They don't actually meet. When will it be when they next meet? Okay.